Hello, students. Today we're going to be talking about proving triangles similar. Mr. Butterworth will be joining us momentarily, but he is not currently available. So we've talked about proving figures similar, and that's what we're really talking about in this first slide, where we have two triangles and we need to decide if they are similar or not. And right now, the only way that we have to do that is to show two things. One, that angles are congruent, and two, that sides are in proportion. So we've got to show that all the sides have the same scale factor going from one to the other. And to do that, we show that by dividing the sides that would go together. I'm going to talk about the angles first. So I've got 60 degrees, I've got 60 degrees, I've got 50 degrees and 50 degrees. And since we know that triangles have to add up to 180, we know that that third angle in both of these cases is going to be 70 degrees. So what that suggests is that both of these triangles have congruent corresponding angles. So in terms of our angles, we are in good shape. Put a check mark there. I don't know why I changed pen style. Okay, so now let's talk about the sides. So in doing this, we also figured out that these are matched up in the orientation that they're in, so that side AB gets matched up with side DE, and so forth. So what we're going to do is to try to divide these and see what we get. So we get 10.5 over 7, okay? And when I do that on a calculator, I get 1.5. We're going to do the same thing looking at our next pair of corresponding sides, EF and BC. And when we do that, we end up getting 6 over 4, which comes out to be 1.5. Okay, looking good. We've got the same scale factor on two of these so far. And let's take a look at the last sides. We've got DF and CA, and those lengths are going to be 4.5 and 3. When I divide those out, I get 1.5 as well. Since all three pairs of corresponding sides have the same proportion, they have the same scale factor, and all three angles are congruent, therefore these two triangles are similar. The last thing I'm going to do is to write a similarity statement to match up the sides that go together. So I'm going to say A, triangle A, and on the other side, 60 goes with 60, so that's going to be D. Then I'm going to use B, which is my 50-degree angle, that goes with E. And then F, which is my last thing that goes on the other one, so C and F go together. And then I'm going to use my similar sign to say that those two triangles are similar to each other. Okay, so the big deal here, kind of like what we did with congruence, we start out having to talk about all 6 pieces, all 3 angles, all 3 sides, and then we started talking about some ways to make that simpler and ways to make that take less time. We're going to be doing the same thing here with similar triangles. So we don't need to show that all 3 angles are congruent to all 3 angles, and all 3 sides are in proportion to all 3 sides. We can show limited parts of that and make our lives a lot easier. Okay, so the first piece that we're going to talk about is something called angle-angle similarity. And the big idea here is based kind of on the definition of what it means to be similar. So we know that similar figures have the same shape and proportional sizes. What this is saying is that there's no way that we can have two triangles have the same angles, but not have proportional sizes. And there are two things that play into this. The first is that with the number of angles that we have, we don't really have a lot of wiggle room in terms of different options. And the third is that if we know two angles of a triangle, I mentioned this on the other page, because we know all triangles have to add up to 180, that means that our third angle must be congruent as well. Sometimes this is called the third angle theorem. It's basically understanding that triangles add up to 180, and if we know two angles of one triangle and we know the same two angles in another triangle, there's no way we can make a triangle that has a different third angle. The other piece of this comes from that these things have the same shape as long as they have the same angles for triangles. So in terms of the minimum amount of stuff that we need here, we need to know two angles, again, which would tell us the third angle automatically, and that will automatically say things are similar. If I jump back for a moment to the picture that we had, if we know that 60 and that 50 and that 60 and that 50 are congruent to each other, what that means is that we wouldn't have to do any of the other work that we did anymore to say that those two triangles are similar. This is a really nice shortcut. All right, so our goal is to decide if these two triangles are similar using this new AA postulate. So AA similarity, we've got to show that two angles from one triangle are congruent to two angles from another triangle. So we've got one angle and another angle that are both 45 degrees. I'm going to say that angle R is congruent to angle V. The other thing that I know going on here is that we have, I don't know why I used two arcs there, that's kind of crazy, but that's okay. We have some vertical angles here. And I'm using two arcs again, so I'm going to make those three arcs. So because we have these angles that are directly across from each other in intersecting lines, these are vertical angles, and we know that vertical angles are always congruent. So for the one on the left side, that's WSR, so angle WSR. And on the right side, that's going to be angle VSB. Now that we know that two angles in one triangle are congruent to two angles in another triangle, we can say that these triangles themselves are similar. And just to kind of match up, so R goes with V, and then we figure out that S is going to go with S. That lines up with the way that they stated these, so we are in good shape. Okay, we're going to look at the same thing. And here we know two angles of triangle JKL, and we know two angles of triangle PQR, but I don't see the same numbers there, so that's kind of weird. Okay, let's first say that this angle here, 70 degrees, must be congruent to this angle here because that's also 70. And then I've got to figure out what this other angle is. So we've got angle K plus angle J. So I'm going to say the measure of angle K plus 30, and then the measure of angle L, which is 70, must equal 180. When I solve that for the measure of angle K, that tells me that K has to be 80 degrees. All right, on the other triangle, and I've got to figure out what's going on over here. So I'm going to do the same thing. We've got 70 plus 85 plus the measure of angle P must also equal 180. All right, I'm running out of space. There we go. That's an awesome 180. I can totally read that. So
Mr.
when
Kaufman, I cannot read that.
Mr. Butterworth,
That does not look like 180.
You're here. That's so exciting. Would it be fair to say that when I solve for the measure of angle P with my easy to read 180, that's going to come out to be not 30 degrees, but rather 25 degrees?
Yes, I would have simply looked at it and said, I have an 80-degree angle and I have an 85-degree angle, so this is probably not going to work well.
That makes sense. But here we've shown that it definitely doesn't work well instead of just maybe. So that's always kind of nice. So I'm going to give this a big nope. And then try to advance and fail. Okay. So now it looks like they're doing the same thing here that we were doing before.
That you were doing. I was not really here.
Yeah, but you were doing it mentally, so that's cool.
Oh, okay.
And one of the things that I notice on the triangles on the right side is that these are isosceles triangles.
That means at least two sides are the same.
That's true. And we talked about something the base angles in isosceles triangles.
Oh, that was the base angles were the same.
Yeah, so if this is 68, that one's 68 too. And whatever this unknown thing is, this unknown thing is going to be the same thing.
That would be
Um,
helpful.
but I'm thinking since we just did two of these together, that these might be good ones for students to try on their own.
That sounds good. Are we going to do the answers for them or leave them open and see if any of them ever ask us about them?
I think we should leave them open and see if any of them ever ask us about them.
I will bet you a shiny 50 cents that
Ooh.
nobody asks us about these questions.
I will bet you a shiny polar seltzer cap that they do.
You have yourself a deal, my friend.
Oh, look, we have another theorem for us to try, or this, I'm sorry, a theorem instead of a postulate.
So we already talked about angle, so now we're talking about side angle side similarity. Now the trickier part about this is we have to look at fractions. That's what this has here. So that makes it like a little bit trickier versus just saying, look, these two angles are the same as these two angles. So we have to think a little bit more. So it's the same idea as the side angle side congruence with triangles, with triangle congruence, try again. But this time it's similarity. So I'll give you an example. If we know that these angles are the same, they're marked the same. If say this side is 5 and this side is 10 and this side is 6 and this side is 12, then we know that the figures are similar because 5 over AB over QR over 10 is the same as 6AC over QS 12 because those can both simplify to 1/2.
Okay, I see that.
And the claim here is that that is enough to show that the triangles are similar.
Now I notice here that the fractions in the book go small to big. I often find it easier to go big to small. Is that okay to do?
Yeah, does not matter. You can do anything you want as long as you are consistent. I had to pay attention also because I didn't know. Theoretically, I could have gone within the two triangles, and I didn't need to go triangle to triangle. But that's a little more confusing, and I wouldn't do it.
And then we've got one more similarity theorem for us to look at, and this is dealing with SSS similarity. So we don't even need to worry about any angles if we can show that all three corresponding sides are proportional to each other. Again, these are all shortcuts that we don't have to show 6 pieces are similar congruent to 6 pieces.
The nice thing about this one is we don't have to worry about the angles. If all we know is the side lengths, which realistically, in terms of actual life, that's the easiest thing to measure.
Yep.
You get a ruler and you say, this is 5 inches, this is 6 inches, this is 8 inches. That's an easy measure. And so I just made up those side lengths. So just to give you the example of AB over RQ is the same thing as AC over QS is the same thing as BC over RS. And I was lazy. I picked the same proportion as before.
Works for me. Okay, so we have some discussion of some indirect measurements, and thank you to Mr. Regis for these beautiful pictures.
They're lovely.
Because they are so lovely. I bet he even counted the number of dots for the stars in the flag, although I'm not going to count those now to double check. I'll assume that
count them and let us know.
Yeah, that's exactly right. So this is
all
all based.
These are triangles.
Yes-ish. I would go one kind of step further and realize that there's some kind of an object in the sky that projects light and causes these to be shadows.
A star.
Yes. And what that tells us is something kind of interesting. That because that is at a fixed angle compared to the stuff on the Earth, which may be a height thing, like these are not a big enough difference for us to notice the difference in angle, but we're not even going to go there. This angle is always going to be equal to this angle. We're going to call that the angle of elevation because we're like elevating towards the sun. No other reason we'd ever use that word. And we also know that assuming that the flagpole is, I'm going to use the word orthogonal to make Mr. Butterworth write the word orthogonal as well. and that the person is standing straight up. These are both right angles. Oh, perpendicular. That's another word for orthogonal. I decided to,
The kids don't know the word orthogonal. Come on, man. So yeah, perpendicular. We're assuming that the flagpole is straight up and down, and we're assuming that the human is relatively perpendicular.
I'm going to add one piece to this and assume the ground is horizontal
Mm.
and that these are at the same elevation.
Well, they're next to each other, so they kind of have to be.
I'm not comfortable with that assumption, but I'm okay with that.
Well, if this is 15 feet, that thing can't be more than like 20 feet away.
We're assuming this is drawn to scale.
I assume everything is drawn to scale.
That's a good assumption.
Okay.
So what we're saying is that the two triangles are similar because of AA similarity.
Does that mean we can set up some ratios?
It does. So like the 15.
Wait, no. How do I start?
You always start with the unknown.
And I'm assuming we're trying to find how tall the flagpole is.
That would be a fair assumption. A lot of assumptions this time, huh?
Well, there's not an actual question.
That's true.
Yeah.
So if we make this a question mark, that works out pretty well. I'm also going to not use yellow.
Yellow. I'll make it in black so you can actually see the question mark.
So
I'm going to call that X. So we have X. I don't know X. And which side does X match up with, the 6 or the 8?
To me, it looks like it matches up with the 6 because that angle that's a right angle is touching that vertical place.
I would also go with conceptually, it is not a shadow. So the not shadows go together and then the shadows go together.
That's pretty fair.
So 15 goes with 8. And now we just have to solve. So I'm going to multiply both sides by 6.
I like it.
And I'm going to get X. I can't write down there. I'm going to write X equals, that's 3/4. So 45 fourths.
Yes.
And cool. The units are feet. So that's like 11 1/4 feet, in case you're wondering. That's not a very tall flagpole.
No, it really isn't. It's also a very low sun. In fact, that would be a 37.5 degree angle of elevation for the sun. But that's okay. 3 for 5.
Oh, because it's a 3, 4, 5 triangle. I was like, how do you know this? Isn't it 36.9? Doesn't matter. All right. How tall is the pile of rocks? I really enjoyed this picture, so I needed to keep it because I don't know how those rocks would be stable, how they're stacked there. But
well, it's because of this one. That one is supporting all of the other ones.
So in this case, this is a mirror on the ground. You're looking down at the mirror so that you can see the top of the pile of rocks, so you can estimate the height. I think that's what's going on here.
I think so too. Because this is a pretty easy thing for us to measure. This is a pretty easy thing for us to measure. Depending on how high the pile of very stable rocks ends up being, that's probably going to be pretty hard to measure.
You could try to climb, but they might fall over.
This also requires a bit more understanding, so using something called the law of reflection, which comes from physics, which a beam of light, which is what we're actually seeing, when it reflects off a mirror, causes the angle of incidence to be equal on either side. In other words, this angle must be equal to this angle.
And if you're freaking out and being like, how the heck am I supposed to know this stuff? We would tell you. Yeah. We would tell you that those angles have to be the same. We would tell you that this person is standing upright and this stack of rocks is perpendicular, apparently. We would tell you that information because otherwise you can't do the problem. We're making assumptions in this video because there's not actual questions here, but that's part of the point of us doing the video.
Point of information, how tall is a pile of rocks? Question mark is a question.
Right, but it's like, there's not enough information given in the picture for us to make all these claims. This is not a good question for us to ask the humans.
That's fair. So in looking at this, I see that we have two angles equal to two angles. So these things have AA similarity. That's a terrible similar sim. And because of that, we can then use those proportion things. So I know that my question mark, which is the upright thing divided by, is that 5.5 feet?
Yes.
Is going to be equal to 12 divide by 4 because those are the horizontal things, and more accurately, those are the included side between the angles that we know about. Therefore, we know those are the corresponding ones. This is going to be, I'm going to use the fun way to do this, that it takes times 3 to get from 4 to 12. So we've got to multiply this by 3 as well to get 15 plus 1.5, which is
16.5. Could I
16.5.
also have multiplied both sides by 5.5?
We absolutely could, and that's a totally reasonable way to do that, and certainly is less weird than using my crazy multiply this to get this thing.
So
And
we
that's
got
all we got.
16.5 feet. We did it.
Woohoo!